In this video, we're going to talk about finding the features of rational functions. And to start with, I have a graph of a rational function here on the left-hand side, or excuse me, the right-hand side, which is x times x minus 2 divided by x times x plus 4 times x minus 3. And let me pinch and zoom a little bit here. And we're looking at this function and saying, well, I see it's showing unbounded behavior. And it's because the graph looks like it has some vertical asymptotes. But other than that, it appears that it continues to go on forever in both directions. And so we're going to talk about the domain of rational functions. The domain of rational functions is the set of all real numbers except for the discontinuities. Now, discontinuities themselves are, if I'm looking at a graph, there are going to be breaks in the graph, but here's the thing is you don't always see your discontinuities. I mean, if I'm looking at this function, I see two discontinuities. I see a break at what looks to be at -4, and I see a break that looks to be at the graph, or at the x value at 3. And so when it comes to finding our domain, we actually have to figure out what the discontinuities are first. Well, discontinuities are the values, when it comes to rational functions, they are the values of x that make the denominator 0. So any value of x that makes the denominator equal to 0 is going to be a discontinuity. Well, if I'm looking at my equation that I have graphed, there should be 3 discontinuities, because I see x equals 3. I see the vertical asymptote in the break at 3, and I see the vertical asymptote in the break at -4, but x equals 0 is, I don't see a break there like I did on the other ones. There are 2 types of discontinuities. There are vertical asymptotes and there are what's called holes. Now, a vertical asymptote is a value of x that only makes the denominator 0. So x value that only makes the denominator 0. So at -4 and +3, I see the behavior of the graph is unbounded behavior. Is what I see graphically. Now at x equals 0, we don't see anything. So I'm going to come over here and I'm going to start tracing on Desmos. There it was. Hold it right there. It says 0 undefined. Well, it's not defined at 0. However, I don't see the unbounded behavior with the graph going straight up and down as a vertical asymptote. There's actually a hole there at 0. We have a hole. A hole is a value that makes both the numerator and denominator equal to 0 at the same time. So it makes both the numerator and denominator equal to 0 at the same time. And in fact, the reason why we cannot see them graphically is because holes are removable. Meaning if I simplified my problem and I'm back to looking at that same equation on the right-hand side, I could cancel out those x's and it would make the same graph. And so it's a removable discontinuity while a vertical asymptote is not removable. In fact, vertical asymptotes are also called infinite discontinuities because they approach positive or negative infinity. And so that's how we defined our domain. We'd find our discontinuities, what makes the denominator 0, and we start constructing intervals around those values. And we can also classify discontinuities as either vertical asymptotes or holes for these rational functions. Now, there's one more thing when it comes to rational functions that we'd want to be looking at, and that is going to be looking at the end behavior. Of rational functions. And we have three scenarios that could happen, all right, where if I'm comparing the degrees of the numerator and denominator. So I'm comparing the degrees of the numerator and denominator. Now the degree just is nothing more than the largest exponent. And we have three scenarios. Scenario 1 means it's going to be bottom heavy. Which means that the bottom has the biggest exponent of x. So I think like y equals 2 over x would be an example. And let's look at what happens for the graph of a rational function where the biggest exponent of x in the denominator. I want to talk about, well, what are the ends of the graphs doing? Pick a color other than black. Now, the ends of the graph, as I keep working, if I keep going to the right forever, or if I go to the left forever, it appears that the ends of the graphs, even if I zoom in to where my vertical scales are one unit apiece, it's approaching the x-axis. So if we're bottom heavy, the end behavior is there will be a horizontal asymptote at y equals 0 at the x-axis. So that's case 1. Now, a second scenario is that they'll have the same degrees. So an example of that would be like the equation y equals 4 times x divided by 2x minus 1. And so we're going to graph that one over here on the right-hand side with Desmos. So 4x divided by 2x minus 1. And I want to look and see, well, what is that graph doing up there? Well, if I zoom out, it is getting flat along the horizontal. So I know that there's going to be a horizontal asymptote looking at that behavior. Now the question is where is it at? Well, if I get on Desmos and I start tracing and working my way to the side and say, all right, let's get way over here around like negative 100. And let's see what the y values are. Negative 1.99. All right, and I keep going. Now I'm at negative 200, negative 0.994, 0.995. They're inching their way closer to the line y equals 2. And say, okay, well, do they all do that? No, they do not all go to the line y equals 2. The rule is, what I do to find the horizontal asymptote is I look at the ratio of the coefficients of the x that have the biggest exponents. They both had the same ones. So the 2 was actually equal to 4 over 2. It's the ratio of the numbers out front. So it's the horizontal asymptote is going to be at the ratio of the coefficients for the numbers out in front. So we have 2 of the 3 cases. Let's look at case 3. Case 3 would be if the function is what I call top-heavy, meaning that the biggest degree or the biggest exponent of x lies in the numerator. So an example would be x squared divided by x minus 1. And let me get my graph back here. All right, and let's graph that function. So x squared times x minus 1, and I look and I say, well, what are the ends of the graphs doing? Well, I'm looking, it looks like it's going along a diagonal line, so it does not have a horizontal asymptote. No horizontal asymptote. Now, to find the end behavior, we would do long division. So we would do long division. But in this video today, we're not going to do that. We're just going to classify and see the horizontal asymptotes either being at the x-axis or at the ratio of the coefficients. And if it's top-heavy, we're just going to say, oh, there is no horizontal asymptote. All right, so those are our key features for rational functions. Now, let's start working on some examples. And I got to back out and get back in here. This thing's acting funny today. And so I'm looking here at number 2. I want to find the points of discontinuity for each one. And we're just going to do this first one here. Now, to find the points of discontinuity, all I need to do is answer the question, what makes the bottom 0? Well, let's just factor the denominator. We'll take the GCF out and say, okay, well, that'd make 4x times x plus 4. Well, there's 2 numbers that make the denominator 0. We have x equals 0 and x equals negative 4. Those are my discontinuities. I don't need to classify them. It just wants to know where are they at. So that's my discontinuities. Now, to find the domain, now I'm going to go over here to number 5. So our goal is to find domain. To find the domain of a rational function, you first find your discontinuities. Which means I have to factor my denominator. So I forget about my numerator and just say, all right, if I want to, I can just write it back up here on the top. And my denominator, I have a common factor of negative 2x. So if I were to pull that out, let's see how that would factor out from there. So if I pulled out a negative 2x, that leaves me with x squared minus 2x minus 3, which that trinomial could factor to be x minus 3 times x plus 1. Now, I look, there's 3 numbers that could make that denominator 0. So my discontinuity points they are at, and I'm going to write them in order in terms of smallest to largest. So I have a discontinuity at x equals negative 1, which is this one here. At x equals 0, that's because of the x. And then at x equals 3, because of the x minus 3 there. Now, to write my domain, the domain of rational functions is the set of all real numbers except for the discontinuity. So I'm going to start with negative infinity, and then I'm going to go to my first discontinuity, which is at negative 1. So I'd go from negative infinity to negative 1, and then I have to use a parenthesis so it's non-inclusive. And then we're going to start a second interval. which says, okay, start at -1, but don't actually use it, get real close to it, and then go to your next discontinuity, which in this case is 0, so -1 to 0. And then start another interval that goes from 0 until you have another discontinuity, which would go from 0 to 3. And then don't stop, because we want to work our way all the way to positive infinity, so we would have to make one more interval and say, all right, we'll go from 3 to as large as we want, 3 to infinity. So that's how we find the domain of rational functions. You find the discontinuities, and then start your way from the left with negative infinity, work your way to the right, because the domain is the set of all real numbers except for its discontinuities. All right? Now, let's talk about how we would find vertical asymptotes. Well, vertical asymptotes themselves are values of x that only make the denominator 0. Only make the denominator 0. Bottom equals 0. So if I'm looking at number 6, to figure those out, I'd have to factor my problem, or I could graph it and look at Desmos. But for number 6, we're just going to factor it. So that would factor to be x plus 3 times x minus 2 in the denominator. Now, there's no way to make my numerator 0 because all that is up there is a 1. So I'm looking and say, all right, well, all values of x that make the denominator 0 then are going to be my vertical asymptotes. So I'd have a vertical asymptote at x equals -3, and I'd have a vertical asymptote at x equals positive 2. Now let's look at 7. So 7, we're still trying to find the vertical asymptotes, which means only make the denominator 0. However, I have a function of x in my numerator. So if I was doing this by hand, I would need to factor this problem. And this would factor to be negative. If I pull the negative out and make x squared minus 4, which is a difference of squares to say x minus 2 times x plus 2. My denominator at this point could be factored to be x minus 2 times x plus 1. Now the rule here is to find the vertical asymptote by hand, it is the factor of x that only makes the denominator 0. Well, if you look at I have two of them. I have x minus 2 and x plus 1. However, the x minus 2 makes both the top and the bottom 0, so that's not going to be my vertical asymptote. My vertical asymptote is only going to be at x equals -1. And I want to look at that graph on Desmos. So let me graph number 7 here. We look, and I zoom in, I only see one vertical asymptote. I only see a vertical asymptote at -1. I'm looking at that scale. Every block is 1 unit. All right. Let's move on, and let's look at trying to find a hole. Now, in order to find a hole, what we would do is we need to fully factor the problem, and holes make both the numerator and denominator 0. So it's one x value that zeroes out both the top and the bottom. Well, if I look at number 8, this is already fully factored for me, and nothing cancels out. So if I can't cancel out a factor that makes the denominator 0, like I can't cancel out the x plus 4s, there's no holes in this one. So number 8, there's no hole. Now, let's look at number 9. So number 9 here, we're still trying to find the hole, if there is one. Let's fully factor this problem. I can take out a GCF of my numerator. This thing is acting crazy. Get back here. All right. Take out a GCF of my numerator, so I can pull out a -3x. I pull that out. That's going to leave me with x minus 4. My denominator, x squared minus 2x minus 8, that I can factor to make x minus 4 times x plus 2. Now that it's fully factored, to find the whole, you're looking for a factor that cancels out both the top and the bottom. Because if there is one, that means there's a number that can zero out both the top and the bottom at the same time. Well, that factor is x minus 4. So x minus 4 is the factor that produces the whole. Well, the number that makes the x minus 4 equal to 0 is when x equals 4. That is my whole. So that is how we determine the difference between a vertical asymptote and a whole for a rational function. Now, the last thing we want to talk about is the end behavior, and we're just going to ask today in this video is what is the horizontal asymptote of each one? And we're going to look at it both graphically, and we're going to talk about our end behavior model rules I talked about at the very beginning of the videos. So if I'm looking at a problem here like number 10, all right, so number 10, I want to see, is there a horizontal asymptote in this problem? Or I'm basically saying, what is the end behavior? Well, I want to look and find x, the largest degree of x in the problem. Well, that is x squared. The degree of x in the numerator is 0. This is a rational function that I say is bottom heavy, because the largest exponent of x is in the denominator. All rational functions that are bottom heavy will have a horizontal asymptote of the x-axis, which is y equals 0. Now, I want to look at this graphically with Desmos. So number 10, we're graphing the equation 3 divided by x squared minus 3x. And I want to look and say, well, what are the ends of the graphs doing here? Well, I start tracing on it, and the farther I go to the right, I'm looking at the y values, it's getting smaller and smaller and smaller. Same thing when I go off to the left. It gets closer and closer to 0, and that's exactly what we have. Now let's look at number 11. So, same thing, we want to know what is the horizontal asymptote, which is the end behavior of the graph. Now, using the end behavior model, we go find the largest exponent of x in the problem. Well, the largest exponent of x is x to the 1 power, and that exists in both the numerator and the denominator. And so, our rule here is to find the horizontal asymptote, because this one will have one, because it's the same degrees. You're going to use the ratio of the coefficients. Well, the coefficients of x to the 1 power, I have a 1 here in the numerator, and I have a negative 3 in the denominator. So it would be 1 over negative 3, or it's just going to be y equals negative 1/3 is going to be the horizontal asymptote. Now, let's look at this problem graphically. So, number 11, I'm going to graph x minus 3 over 3x, or excuse me, negative 3x minus 3. We graph it, and we want to look and say, well, what is it getting close to? And I see that it does get beneath the x-axis here. Now, I'm going to start tracing and see. I'm only at negative 0.294. And let me get farther over here to the right. Negative 0.325. Negative 0.327. So it's inching its way closer and closer and closer to negative 0.3 repeating. Now these problems are almost easier to do by hand than they are to type them in and look at them graphically. All right, now I want to look at number 12. So number 12, define the end behavior, or determine if there's a horizontal asymptote, because that's what we're trying to figure out. You go find the biggest exponent of x. Well, the biggest exponent of x is x squared. Both the numerator and the denominator have it. So since both the numerator and the denominator have that highest degree term of x, there will be a horizontal asymptote, and it's going to be at y equals the ratio of the coefficients again. Well, I have a coefficient of the x squared of 2 in the numerator, and I have a coefficient of 1 in front of the x squared of the denominator, which means the ratio of the coefficients, 2 divided by 1, means that the horizontal asymptote should be at y equals 2. Well, let's confirm that graphically. So here, we're going to graph that expression, 2x squared plus 8x divided by x squared plus 2x minus 3. And I want to see what are the ends of the graph doing. Now, I don't care about the middle. This is a end behavior asymptote. And so I'm going to zoom way out, and I'm going to get on the curve, and I'm going to trace. And I start working my way to the left. I'm at negative 1.982, so that's getting pretty close to 2. And when I'm working my way to the right, I started off bigger than 2, but as I work my way to the left, I'm working my way back closer to 2, as we can see. All right, so that is my horizontal asymptote. Last problem here, number 13. So number 13, I want to determine, is there a horizontal asymptote? We go find the highest degree of x, which is x squared, and the only place that has it is in the numerator. This is top heavy. If the numerator has the highest degree term of x, there will be no horizontal asymptote. All right, so let's look at that on the graph. So I'm graphing that expression, number 13, x squared minus 3x divided by negative 4x minus 4. And I'm zoomed way out here. All right, so when I'm zoomed back in, we can see how it's got its vertical asymptote. But when I zoom out, notice how, and I make it a square zoom, notice how the ends of the graph are not getting flat along the horizontal. They